let's consider what happens when we have an object that's moving on a horizontal surface. So here's our object, and here's our surface. Now we want to look at a special case where we're applying a force F to the object, and the object is moving at a constant speed. Then what we see here is that there has to be some type of force that's opposing this object, interaction between the object and the surface, that's distributed over the surface. For this, I'll write an arrow here to express that force. That's the tangential component of the force. The object is also pressing down on the surface is pressing up on the object, and so there's another perpendicular force to the surface, which is referred to as the normal force. And the total vector sum of these two forces, the perpendicular part, the normal force, and the tangential part, is referred to as the contact force. This is what we'll call kinetic friction. Now, when the object is moving at a constant speed, we know that from experiment that the kinetic friction, the magnitude, is proportional to the magnitude of the normal force, and the constant of proportionality is called the coefficient of kinetic friction. Now, this law is telling us something very interesting, that two key properties are, one, that it's independent of the contact area. Now, what do we mean by that? So let's look at the following picture. Suppose we have two objects of the same mass. On the surface, we're applying a force F, and the contact area here, A1. And we have a similar object, the same mass, on the same surface, and both objects are moving at a constant speed. Now, these objects have different areas of contact, A1 and A2, but the force necessary to move the object at the constant speed is the same. And because of that, the kinetic friction is the same, and that indicates that it's independent of the contact area. And the other key property here, which we'll write over here, is that it's independent of the speed of the object. So we'll write that as independent of the velocity. And these three properties of kinetic friction are crucial for understanding the motion of objects across a surface, but we still don't have a very good theoretical model for explaining this, although today there's a lot of contemporary research which has made a lot of progress in understanding this interaction. We consider the case where an object is moving along the surface, but now let's consider what happens that if we apply a force F here and the object stays at rest. Well, we still have the normal force distributed over the surface, but now because the object is at rest, there's another, the contact force now is what we call static friction, the tangential part of that. And the contact force is still the perpendicular part, the normal force, plus the tangential part, which we refer to as static friction. Now, what happens with static friction is that if we don't apply a force at all, then there's no static friction. In fact, you can see in this simulation that if we slowly increase the applied force, then the static friction force gets bigger and bigger. It depends on what we're doing to the system. But at a certain point, when we apply a large enough external force, the object suddenly starts to slip. That's what we call the just slipping condition. And the reason for that is static friction has reached its maximum possible value. That has to do with the physics of the interaction between the surface and the object. So also there's a very subtle thing, is that as you see when we pull the force and it just slips, suddenly the friction has gone from static to kinetic friction, and it's gotten a little bit smaller. How do we express those properties? Well, what we have is the idea that the static friction can vary in magnitude, between 0 and some type of maximum value, depending on the other constraints on the system. And the maximum value of static friction, we have a force law, which is that it's again proportional to the normal force, but the coefficient is called now the coefficient of static friction. And this coefficient of static friction is slightly bigger than the coefficient of kinetic friction, which explains why that arrow got a little bit smaller when it just started to slip. Now, again, like kinetic friction, static friction is opposing this external force. And depending on the direction that the object moves, for instance, if we applied the external force in the opposite direction, here, then the static friction that's distributed over the surface is opposing that force. But there may be many systems in which we're actually not quite sure which way static friction points. And as the course develops and we look at more complicated examples, we'll see that the direction of static friction can depend on all the other constraints on the system.